Okay, I think we can begin. Professor Emma Hill really needs no introduction. Introduction is also here. I'm Lee Suing. I'm the director of the Institute of Advanced Studies. In the past, Institute of Advanced Studies has been running programs using a lot of academics from outside NTU. So what I'm doing is that I'm bringing the focus back onto our excellent scientists and mathematicians in NTU. So we try to do about one seminar per month, and this is the third one in the series. Okay. Now, Professor Emma Hill joined NTU in 2010.
Yes.
And in 2011, she was awarded the National Research Foundation Fellowship, which is a prestigious fellowship for young and upcoming academics. She did her PhD in US in geophysics. And then before joining NTU, she spent a postdoctoral stint at the Harvard Smithsonian Center for Astrophysics. Yeah. Her PhD is in geophysics. Recently, she has been awarded the Singapore National Research Foundation Investigatorship, which is a very prestigious and very much sought after investigatorship.
Thank you.
So this year we have 3 NTU scientists who have been awarded this National Research Foundation Investigatorship, including Professor Emma. Okay, now her work is in the area of space-borne geodesy. Actually, I didn't know what geodesy was all about, so I surfed the internet this morning. So it's a branch of the Earth sciences, I believe,
yes.
And uses a lot of applied mathematics and modeling, right?
Yes.
To understand the curvature or the Earth's surface. Okay, so today she's going to share with us this very important topic in this region because, as you know, in recent times we have had a lot of disasters and earthquakes, tsunamis. So her topic this afternoon is on space-borne geodesy and remote sensing for understanding natural hazards, sea level change, and disaster response in Southeast Asia. Emma?
Thank you. Thank you. Can you all hear me okay? Okay. So I can expand on that definition of what geodesy is in case you also don't know. I don't know if, I hope everyone can see the bottom of these slides, but the official definition is that geodesy is the study of the size and shape of the Earth and its gravity field and how these things change over time. So it's actually one of the oldest fields of science in a way, because it goes all the way back to the ancient Greeks figuring out that the planet was round, not flat, and what the radius was and things like that. So for quite a long time, it maybe was a little bit boring, but in the last few decades, with the launch of space-based geodetic techniques, we can measure these things with really high temporal resolution and really high spatial resolution. So it's a field that suddenly got kind of launched into this very interdisciplinary science. It's observing all kinds of Earth processes, such as earthquakes, volcanoes, sea level rise, melting glaciers. These are all things that can change these parameters if you're able to measure them accurately enough. Okay. So in this talk, I'm going to talk about 2 types of geodetic data. The first one is the Global Navigation Satellite System, or this was originally GPS, the Global Positioning System, now expanded into various constellations launched by countries other than the United States. It's the same as what you have in your cell phone or your car, except that for us, we take very high precision receivers, very high precision antennas, and we bolt them into the ground, and then we leave them out there recording continuously every 1 second. And so they're continually recording their position, and so they're continually recording how the surface of the Earth changes its shape according to earthquakes and so on. The other type of data that I'm going to talk about is synthetic aperture radar or imaging radar. And I'll tell you more about both of these in the next few slides. One of the things that I want you to go home with is to know that these were launched with positioning intentions, but in the last few years, we've developed all kinds of new innovative ways to look at the data and process the data. And so what were positioning devices are now kind of all environment sensors that can observe actually all kinds of different and interesting things. We installed a lot of stations so EOS installed a lot of stations around the region. We have about 100 of these guys in Indonesia, Bangladesh, Bhutan, India, and Myanmar. And we put them in originally so that we could measure tectonics and earthquakes, so that we could measure how the Earth's crust is deforming as a result of the tectonics. But what I'm going to show you is that we can actually use them to study climate and vegetation and all kinds of other things too. And then I'm going to give some examples of work that we're doing to help the region be more resilient against natural hazards and disasters by using these types of data to monitor the hazards and also to map disasters after they happen. Okay. So what do I mean when I say that the GPS system can actually be far more than a positioning system? Well, over here is the kind of more traditional uses. And so we use it to record the position every minute, and then if we put one on a volcano and it starts inflating, then we'll record that. If we put one near an earthquake fault and there's an earthquake, it will suddenly move position and we'll record that. And so we can study those earth processes. But the GPS signal has to travel through the ionosphere. So in the past, this was our noise for getting accurate positions, but now we can use these observations to study atmospheric processes. And then it turns out that another source of noise, which is that the signals don't just travel directly from the satellite to the antenna, but they also bounce off other surfaces first. And it turns out that we can actually learn about the surfaces that the signals are reflecting off so that we can study things like sea level change, changes in snowpack, changes in vegetation moisture content, and changes in soil moisture. Imaging radar it's an active sensor. The satellites put out a microwave which bounces off scatterers on the Earth's surface and back up to the antenna on the satellite. And the fact that it's active makes it very valuable for the tropics, because unlike optical data, it can see through clouds and it can see at night. So you just have to look out the window to know that optical data is not particularly useful in the tropics a lot of the time. And especially if you want to study things like floods. Well, floods come with clouds, and so it's often very difficult to image them with optical sensors. So with synthetic aperture radar, day and night, we can make observations of the Earth's surface. So what I'm going to do in this talk is that the next few slides will give you some of the theory for how we can observe these different quantities with GPS and with SAR. And then I'm going to give you examples of the applications of this, mostly from our work in Southeast Asia. So here's the traditional way of using GPS. It was launched by the US military as a timing and positioning device. Timing because the satellites have very accurate atomic clocks on them, and positioning because if you have a receiver on the Earth's surface, it can record the time that a signal takes to travel from the satellite to that receiver. And we know exactly where the satellite is. And so we know just from that one observation that our position must be somewhere on a sphere around that satellite, because we can just multiply the travel time by this approximately the speed of light and get the distance. And then if we observe to enough satellites, then it's a trilateration problem. So we just need to look at where all of those spheres intersect, and we can estimate our position. So this is how GPS was originally used. Of course, it's a bit more complicated than that because the signal isn't just traveling through a vacuum. It's not traveling exactly at the speed of light. It's traveling through the Earth's atmosphere. And this can result in delays in particularly two different parts of the atmosphere. The first one, I didn't know I was going to get a soundtrack. Sorry, I'll try not to be distracted. Okay, so the first one is in the upper atmosphere, and this is the ionosphere. And this is the upper part of the atmosphere. It's what generates the northern lights. And there are all these free electrons floating around up there. These slow down the GPS signal, so they impact positioning. But the good thing for us is that the amount that they slow the GPS signal down is linearly proportional to the wavelength of the signal. So the designers of GPS were smart, and they send the GPS signal out at two different wavelengths. And then it's simple algebra for us to calculate how much the signal is being delayed by the ionosphere. And for positioning, we use that to correct the positions. For a long time, that was just something that we threw away. But recently, we've realized that actually that's a measure of the electron density of that part of the ionosphere that the signal has traveled through. And it's a way for us to study space weather, ionospheric tsunami, I'm going to tell you about, and other phenomena. My group are not actually studying space weather, but this is something that there are people at EEE who are interested in collaborating with us on. The other part of the atmosphere that causes delays to the signal is way down at the bottom, and I'm afraid some of you may not even be able to see it, but in the troposphere, which is the 10 kilometers or so above where we live. And in the troposphere, there's water vapor, and that water vapor delays the signal. There's not a really easy way to estimate and remove it, but we can just treat it as an unknown parameter when we estimate the GPS position and get an estimate of how much water vapor is in that part of the atmosphere. And so we can use that to study climate and weather. And then the final new innovative processing technique that's come about really just in the last few years is to take these, what we call multipath reflections. So the ideal scenario for positioning is that you only record the direct path from the satellite to the receiver. But the reality is that other paths bounce off reflective surfaces near the antenna and arrive at the antenna. So for positioning, this path is longer than the direct path, and it will give you an incorrect position. And that's really difficult to correct for, in fact. But the neat thing about this is that most GPS receivers, or high precision ones, also record the signal to noise ratio, just historically so that we had an idea of how strong the signal was. When you get a situation like this, the direct signal and the reflected signal interfere with each other. And this interference results in an oscillating wave in the signal to noise ratio time series. So if you plot signal to noise ratio over time, it looks like a sine wave. And there's actually a beautifully elegant equation how to describe that, which I've put up here. And it's a function of the height of the antenna above the reflecting surface, and also the A is the amplitude term and phi is the phase term. And these are a function of the reflecting properties of this surface. So things like the dielectric constant if this is soil. And so we can actually use this information to learn about any changes in the distance between the antenna and the reflective surface, and any changes in the reflecting properties. And they have known effects. Like if you just have regular bare soil, then your signal to noise ratio might look like this. But if you then add a snow layer so that you increase the height of the reflecting surface, then you change the wavelength, you change the frequency of this oscillation. If you add vegetation, you just overall reduce the signal strength, and so you reduce the amplitude of the signal to noise ratio curve. Or if you make the soil wet, you change the dielectric constant, and so you actually change the phase slightly of those signals. This one is actually really difficult to measure. Okay, so those are my applications of GPS that go far beyond positioning. Then I have a few slides on the theory of synthetic aperture radar. And so in geodesy these days, we're interested in change. We're interested in how the Earth's shape is changing shape over time. So what we want to do is use repeat pass imagery. And with satellites that have really well-controlled orbits, such as the European Space Agency satellites, which are called Sentinel, they repeat every 6 days, and every 6 days they come back to the exact same position, and they record exactly the same area of ground. And if everything else is equal, then the path length from the satellite to each pixel in the image is going to be the same from one scene to the next scene. And so it's going to be exactly the same number of wavelengths and then the exact same piece of wavelength, the phase. And so the difference in the radar phase from one scene to the next is going to be 0. If something changes the location of these pixels, such as like in this image, there's been an earthquake, so I've moved the pixels, then the path from the satellite to each pixel changes, and the phase that we record changes, so there's a phase difference. And in INSAR, interferometric synthetic aperture radar, we map the phase difference for each pixel, and we can use that to map changes in the shape of the Earth's crust in that region. So this is how we've been using INSAR for the last 20 years or so. In the last few years, then there have been a number of developments. These were made by our collaborators at JPL. And the first way is, so in the previous one, it assumes that all the scatterers in each pixel kind of stay the same. So the radar phase arrives and there's all things in the pixel like cars and buildings and whatever. And it's assuming that they mostly are the same. And there's going to be some that are oriented nice and perpendicular to the incoming radar wave. So they put a very strong reflection back. Some might not be optimally oriented. So it's going to send the signal off into the other direction and make the pixel a little less bright. But overall, from week to week, the items in each pixel pretty much stay the same. We don't have massive changes. If the contents of the pixel really dramatically change, then we can't track the phase anymore. It becomes incoherent. And so for the previous technique, for the INSAR technique, it's noise. We're just like, oh no, the contents of the pixel change too much. We can't map the change in the position of that pixel anymore. But often if there's been a disaster, like an earthquake, the reason that the pixels changed so much was because buildings fell down. And so the reason that we suddenly can't track the phase anymore is that there's building damage. And so the non-conventional use of INSAR is to plot the noise after a disaster and relate that to building damage. I'll show you an example of that soon. The other way that we can use synthetic aperture radar somewhat non-conventionally is to look at not the phase, but the amplitude of the signal. So basically just how bright are all of the pixels in the image. And on a regular dry day, you're going to have some scatter. The scatterers in each pixel have different orientations, but there's going to be enough that they send signal back in the direction of the satellite. If you then flood that area, then the floodwaters act like a mirror. And so the signal bounces off it and just goes off in the other direction. And that pixel goes from relatively bright to completely dark. No microwave radiation is returned to that, for that pixel. It's a little bit more complicated than that, because if there's features on the ground like buildings or trees, you get this double bounce. And So this is an area where we're actually trying to apply machine learning, because there's no good equation to depict how items on the ground will actually interact with the radar wave. But in theory, we can use changes in the amplitude of the SAR signal from before a flood and during a flood to map the flood. Okay, so that's the theory, and I've described there 2 different geodetic observing techniques, but about 10 different ways that we can use those geodetic data to study different parts of the Earth system. And so I'm going to go through some examples of those. First, I'll talk about earthquakes and tsunami, and then sea level, climate, and finally I have, I think, 1 slide about volcanoes. So this map here shows Sumatra, excuse me. All of those white dots are continuously operating GPS stations. We call this the Sumatra GPS Array, or SUGAR. And some of these were installed back in 2002, and they've been recording ever since. At Sumatra, the Indian-Australian tectonic plate is diving underneath of Sumatra. This is a subduction zone. And the contact area between these 2 tectonic plates is what we call the Sunda megathrust, this surface here between them. And because rocks are not beautifully smooth, there's friction on this surface, and so they get stuck. And so for about 200 years in this area of the world, this is stuck. The 2 plates are pushing together from a distance, but along the joining surface, they're stuck together. And it takes about 200 years to build up enough stress to overcome friction. But when you overcome friction, it suddenly slips forward. And that's what generates seismic shaking and an earthquake. And so these instruments are there because when it's stuck together, this is all being dragged down by the downgoing plate. And then in an earthquake, they pop back up again. And we can record both of those types of movement. Here's an example of what it looks like for one earthquake. And if you're not an earth scientist, I will help dissect this figure for you. So let's start with, so the blue vectors are the displacements during the earthquake recorded by our GPS stations. So you can see that for the nearby stations to this earthquake, the earthquake started here, there's about 20 centimeters of displacement. For the larger earthquakes, this was a 7.8. For the larger earthquakes, like a 9.2, these displacements will be many, many meters. In some areas, many tens of meters. The colors are they're the surface projection of slip on that dipping surface. So the amount that this surface slipped, I've projected it onto the surface. And we can make numerical models that relate how much these displacement, if a station moves this much, it's due to slip of this much on the fault, or vice versa. If the fault slips so much, then the stations will move a particular amount. So we can go either way. We can do an inverse problem where we know how much all the stations slipped, and we can solve for how much and where the fault slipped. And it's because these are recording their position every single second, they're almost like seismometers, but better. Seismometers just record shaking, but GPS receivers record both the sort of more permanent displacement that's going to take another 200 years to undo, and then they also record all the seismic waves. And we can use that information to solve for how much the fault slipped. And what we can do, we can do this for all the earthquakes. Sumatra has been particularly busy. So what you see in this figure are estimates of slip for all the large earthquakes in Sumatra since 2004. This is useful for understanding earthquakes, but it's also useful for humans because it allows us to see where the seismic gaps are. And we can see that this part of the fault has not yet slipped. So this area is forecast a great earthquake we expect that at some point in the next few decades, we can't say any better than that, but at some point in the next few decades, it's going to see a big earthquake generated from there. That's very scary because the tsunami that it would generate will hit the city of Padang, which is about 1 million people and very low lying. So the GPS are also useful because we can try and monitor this and see if we see any changes in the behavior of the fault. When the fault slips under the seafloor, it lifts the seafloor up during the earthquake. And then that lifting the seafloor up lifts up the water column above it. And that then has to go somewhere. It generates what we call a gravity wave. So that water has to flow. And it flows across the ocean in a very long wavelength wave. Something kind of interesting is that it doesn't just lift up the water column, but it actually lifts up the whole atmospheric column above it, which is a lot less dense than water. And so it doesn't just create a water tsunami, but it ends up creating an ionospheric tsunami too, where you lift up all the electrons in the ionosphere and then they have to flow. And GPS actually measures the content of electrons in the ionosphere. So we can record with GPS not only how the ground moves, but we can also record the ionospheric tsunami. And we asked ourselves, could this actually be useful for tsunami early warning? The reason we thought that was because, so water tsunamis, when they're in the deep ocean, they're not particularly dangerous. The reason that they get dangerous is that when they get close to the coast and the seafloor gets shallower, the friction between the water and the seafloor slows that wave down. And because it's such long wavelength, it piles up, and gets very big. In the ionosphere, there's no shallow coastal bathymetry to slow it down. And so the ionospheric tsunami just happily keeps on going at about the speed of a jet plane without anything to slow it down. And so in terms of land-based observing networks, the ionospheric tsunami is going to arrive quite a lot sooner than the ocean tsunami. And ionospheric tsunami is not going to cause humans any trouble. So we wanted to do an experiment with that with our sugar network. And in 2010, Sumatra created a very nice natural experiment because it gave us 2 earthquakes of the exact same magnitude, recorded by the same network, but they were very different. This one happened deeper on the megathrust, down deeper on that surface, and this one was very shallow. And because this one was very shallow, it created a very big tsunami. It killed about 600 people. And it was the tsunami warning systems failed because it was so far from the coast, and the tsunami it generated was much bigger than they expected based on that magnitude. So we asked ourselves, could just the GPS ionospheric information have told us that this was a really dangerous tsunami and this didn't really create a tsunami? And the answer was yes. The top 2 figures are for the dangerous tsunami, for the one further south, and then the bottom 2 ones are for the one in the north, which didn't cause any damage at all. And the line graphs are a time series of electron content, of electron density. They have different y-axes, so you can see that at some point after the earthquake, which is the red line, there was a pretty big signal. And then these are in the frequency domain, and you can see this dotted line here is about where we see, that's just background noise from solar flares and things like that. And then about 8 minutes after the earthquake, you see this really big signal. 8 minutes is how long it takes for the acoustic wave to travel from the source of the earthquake up into the atmosphere and allow us to record it. So it seems like it could actually contribute to tsunami early warning systems as an extra piece of information. We can also use INSAR to study earthquakes. Here's an example where, so interferograms are kind of weird to look at when you first see them, but basically every set of rainbow fringes is a displacement of that pixel at the wavelength of the SAR satellite. And in this case, the wavelength is 22, 23 centimeters. And you can see here that the earthquake actually started here in the city of Palu. This is the earthquake on Sulawesi last year. And then it ruptured down here, and it ruptured all up here. So that it broke a big line all the way along here. And so all of these rainbow stripes are showing motion from that earthquake. And we can do similar modeling to how we do with GPS to figure out exactly how much the fault slipped and where. This is the same earthquake, but instead of plotting the motion of the pixels, we've plotted basically the noise from that previous slide. And so all of these red areas, this is the city of Palu here, are where we lost SAR coherence. So these we can interpret as building damage. And we actually provided this to, we validate it with information from the ground, like knowing, yes, okay, that pixel is red and a bridge fell down and so on. We provided that to emergency responders, and it was actually used in coordinating the disaster response for this earthquake. This was our first foray into disaster response. We were helped a lot by people at JPL, but that's something that we're hoping to do more of in the next few years. Okay, so that was my tectonic section. Moving on to sea level. So I explained before about how the frequency of the oscillations in the signal-to-noise ratio recorded at a GPS station are reflective of the difference in height between the reflecting surface and the antenna. So if we track the changes in the frequency of that oscillation, we can actually track differences in parameter h. And a project that we have now is that we're installing the first GPS network anywhere in the world specifically designed to measure sea level. And a really nice thing about this is, so if you have the traditional way of measuring sea level is you put a tide gauge you put it in the water here, and a tide gauge will record a change in relative sea level either if the sea surface height changes or if the land height changes, and you can't know which it is. And in this part of the world, because we have tectonics, because we have subsidence from reclaimed land, subsidence from withdrawing groundwater, there's a lot of reasons that the land heights are not stable here. And we can't really extract which is which from a tide gauge. With GPS, we can estimate the height of the sea surface from the reflected signal, but we can also use regular traditional processing techniques to estimate the vertical changes of that station. So we can pull apart those two different things. What is due to the sea surface height changing, which would be climatic effects, melting glaciers, warming waters, and so on, and what is from tectonics and other land processes. And here's an example of how well it works. So the solid line in this figure is from a tide gauge at this site, and this site has really, really big tidal variations. And the solid line is what you would record from a tide gauge, but the colored triangles and the squares are what we record from a GPS. And you can see that the GPS from the multipath reflections does almost as well as the tide gauge for recording sea level change. Here's one reason that we need to care about these land height changes, and this is an example using SAR, imaging radar. This shows rates of land height change for the city of Jakarta in Indonesia that we observed using imaging radar, using the INSAR technique. And there's 3 colored arrows corresponding to 3 colored time series here. And these show subsidence in Jakarta of about 20 centimeters per year. And I'm not getting the units wrong. It's 20 centimeters per year. So every 5 years, Jakarta loses about a meter of elevation. It's a big mess. So this is a neighborhood that when we visited it, actually they were evacuating that neighborhood completely because it was pretty much permanently flooded. People were living on only the upper floors of their houses. Jakarta is the worst in our region, but a lot of the major cities in Southeast Asia are sinking as a result of withdrawing groundwater too fast. Basically, you pull out the water, and the water helps to hold the sediments, the soil sediments. It gives them strength, and you pull out the soil, and then they can just be compressed. So one of the things that we're going to try and do in the next few years is to do this kind of analysis, but for all the coastlines of the region, because we need to incorporate those into projections for sea level change due to climate if we want to actually plan properly. This is not work that we're doing here, but I put it in just because I think it's cool, and it is a very nice application. In this example, there's a GPS antenna up here, and the blue lines are tracking changes in the height of the reflecting surface, which in this case is snow. So they're tracking changes in the depth of the snow. The red triangles are where some poor person, maybe they're not poor, maybe they like cross-country skiing, but somebody went out and stuck a stick into the snow every few days and recorded a point. And you can see that they track very nicely. So there's other groups now are trying to put GPS in places like Antarctica to track changes in glacial snowpack. The technique of studying changes in the height of the sea surface is good for studying long-term sea level rise, but it's also really nice for studying storm surges. So same deal, that we look for changes in the frequency of the SNR oscillations, and traditionally these would be maybe observed by a tide gauge, but usually because it's a storm surge, the tide gauge gets destroyed. And so there's very little information actually on how big storm surges are. With GPS, you can put it high up on a building and it works just fine. And so it's not destroyed by the storm surge. And so here's an example where there happened to be a tide gauge that was not destroyed for a typhoon that hit Hong Kong last year. And we plotted the tide gauge data in red and then the GPS data in blue. And you can see here that this was the first time anyone captured a storm surge using a GPS instrument. This one is also not our work. This is work being done in Colorado, but just in case there's anyone interested in ecology or droughts, then just to show that the reflective data, if you track the phase of those oscillations, can track quite nicely soil moisture. So this is soil moisture from an in situ probe, and this is an estimate from GPS. And these guys are actually trying to put out, they now have like a publicly available database that shows changes in soil moisture for many, many stations in the United States. And theoretically, we could do this kind of thing with our networks also. So this figure somehow got messed up. This was a map showing our stations in Myanmar, India, Bangladesh, and Bhutan. We have about 40 stations in those countries in total. And this is a nice example of how we can look at changes in hydrology also from just looking at the position. And the reason that we can do that is anytime the Earth's crust is elastic. It behaves elastically. So anytime you put a really big weight on it, such as a large amount of water or a glacier, then it pushes down on the Earth's crust. So the Earth's crust bends down. If you then remove that load, then the Earth's crust elastically responds. Our GPS stations record the response of all the weight of the Indian monsoon on the continent every season. And so what those time series show are all of our stations to the north. And this is the vertical component of the position. And you can see a very nice seasonal signal in that. That is from the weight of the monsoon waters. And we can actually, we're working on it now, but we can actually make estimates of how much water it was that pushed down the Earth's crust for any particular year. You can do that seasonally. You can also do it long term. This is an example for the Western United States, where what they did was, you can see in 2014, just this very long-term uplift of the entire Western United States. And that's a result of the ongoing drought there. If you keep in mind that figure for 2014, and then I flick onto here, you can also see that same drought, but recorded in vegetation moisture content. So you can see for all those same GPS stations, this is our collaborator in Colorado again, what she was able to do was track changes in the amplitude of the signal-to-noise ratio and show that the vegetation is getting drier and drier in that area as a result of the drought. Okay. Also in terms of climate, this is something that we realized quite recently, is that these stations that we installed to measure earthquakes and tectonics are actually kind of weather stations. And they're quite long-running weather stations. We've had them in now for about 15 years. And these figures are showing water vapor recorded by our stations, basically tracking water vapor in the atmosphere due to the Indian monsoon. So the blue line is the monsoon index, and the red line is, we've done principal components analysis to pull this out, but you can see that the water vapor content recorded by the GPS matches quite nicely the water vapor of the Indian monsoon. Okay, I think this is my last slide on weather. This is an example of how we can use changes in the amplitude of the SAR signal to map floods. So all of this was for the Laos dam collapse last year, and up about here, there was a hydroelectric dam being built by a Korean company in Laos, which collapsed. And all of these red pixels are pixels that in our SAR image went from dark to bright, meaning that before there had been water reflecting the signal off in the opposite direction. And then after the event, then it was dry, and so more signal was returned to the satellite, and the pixels became brighter. On the other hand, all of this blue is where the SAR returns went darker. And so in those signals, they were dry, and then they got flooded, so the signal bounced off in the other direction, and it got darker. This is also something that we sent for emergency response. So it was used to help see which images were flooded, and it's something we're working on how to do this more accurately in future using machine learning. But it's a really important part of what we're doing, because there's so many floods in this part of the world that we need to help with. And then for my final application, I added this in just in case there were any volcano people in the room. But looking at the signal-to-noise ratio of the GPS can also be interesting in that it can detect ash in the atmosphere due to volcanic eruptions. And this is really important for aviation, because you don't want to fly an airplane through a volcanic ash cloud. And often, because there's so many there's thousands of volcanoes in this region, they're not all monitored, then it can sometimes be that a volcano erupted and we didn't know about it initially. Benoit at the EOS is working more on how to do early warnings of these. But if you have a volcanic eruption, then any GPS signal coming through it will lose some power, and so you'll see a reduction in signal to noise. And here's an example for a volcano in Alaska where the signal to noise ratio was suddenly dropped. And so this is a case where we can hopefully in the future use our GPS networks for something other than tectonics. Okay, this is my final slide other than this summary, but I just wanted to give an update in case there are people in the room who are working on big data and data analytics and machine learning. You can imagine that the data volumes that we're dealing with are pretty huge. And they're dramatically increasing every year. Like in the next few years, the Finns are going to launch a SAR satellite. The Japanese are going to launch a second one. The Americans are going to launch one. And so, and it's terabytes of data, petabytes of data, massive amounts of data. And so, and the GPS are recording their position every second. That's also massive amounts of data. Our way of operating so far has been that I hired a postdoc and they did the SAR processing, and it was all pretty manual. But in the last 6 months or so, we worked with JPL and Caltech, and they built a system that will process these data in the cloud. So it's very, very scalable. So we can suddenly process 8,000 interferograms in the same amount of time that we've been able so far to process one. And so in terms of my NRF investigatorship, a big part of it is just now figuring out how to deal with a lot more data, since we have this processing system now installed at EOS. We're the only ones that they've agreed to do that with, and the reason that they agreed was because JPL and Caltech are sitting very close to the San Andreas Fault, and we promised that if there's an earthquake, then we will help make the disaster response maps for them, because they may be otherwise occupied at the time. And then they also, because this can be used particularly to process SAR data for disaster response, they also were interested that we can take advantage of the time difference to make operations, people don't have to lose so much sleep if there's a really big disaster. So we're going to expand our processing to be much more regional, and we're definitely looking for collaborators, for people in other groups who know how to deal with big data. Okay, so yeah, I hope I've persuaded you that with a little out-of-the-box thinking, we can take two observing systems that were designed to do pretty much just one thing, and we can do a whole lot of other things with them. And they really can observe many different components of the Earth system, which is also just important in that with a system as complicated as the Earth, we need to think pretty holistically. An earthquake will result in sea level change, for example, because it changes the height of the land. So, yeah, in the next few years, we're going to be processing a lot more of these types of data, and also trying to figure out better ways to quickly and accurately use these sources of information to help with disaster response in Southeast Asia. Thank you.
We have time for some questions for Emma.
Yeah, very interesting talk. Thank you very much for that.
Thank you.
I suppose, but you didn't have enough time for that. But what would be interesting is to get a bit of a feel for what those new methods add to the existing network of observation, because for many things, there are things already out there to observe. I'm thinking sea level rise, for example, sea level. There's plenty of other way to look at that. So what in particular the network of GPS is adding to the ability to observe? Is that coastal, near the coast? Is that where things are really more precise?
So for sea level, surprisingly, there's actually very little data in terms of tide gauges for Southeast Asia. The Indonesians do have some tide gauges, but they're not publicly available. So our stations are potentially some of the only tide gauges in the region. The main advantage of GPS for sea level is that you record the land height change in the same observation. So with the tide gauges, it's been really difficult for Southeast Asia to assess how much sea level rise we're seeing as a result of climate change, because all of the land dynamics make the tide gauge records that we do have quite messy. In terms of the other observations, so one where GPS can really add something is water vapor. There are very, very few, I'm not an atmospheric scientist, but as far as I know, there's very few ways to actually observe water vapor in the column of the atmosphere, and it's not something yet that's routinely absorbed into climate models, is the volume of the quantity of water vapor. What else did you
I was more thinking about the satellite. We observe the sea level, but seems to be struggling next to the coast. Is that really?
So yeah, the satellite altimetry will give you sea surface height, but that struggles near to the coast. That's actually it's also a radar, but the footprint is big enough that near the coast you've got some land and you've got some water in the same beam, and it's pretty difficult to get an accurate measurement near the coast. Yeah.
Singapore has a Center for Remote Imaging, Sensing and Processing at NUS. Are
Yes.
you doing similar work for,
Short answer, no. Mostly they're doing optical work for military purposes. Then, yeah, they're not using radar, and they're not really doing any. They're also doing some work doing kind of land use classification across the region, but not so much the earth science processes.
I'll ask another question then. Monitoring soil moisture, how deep that actually the signal is being picked up? How much of the subsurface are we talking about here? And second question, you show example from overseas. Are you close to have something for the region that will monitor soil moisture here in the region?
So yes and no. We have the data. We haven't tried very hard at all to do it. I had a student look at it and she was just like, oh, this is really complicated. One of the biggest problems with soil moisture is you have to have a really nice flat open space around your receiver, and so you can get easily messed up because there'll be like concrete and then vegetation and you don't quite know what you're measuring. In terms of how deep, I think you can go about 20 centimeters. The depth will depend on the moisture, but GPS is L-band, so the wavelength is about 20 centimeters. So I think you can penetrate about 20 centimeters in. It'll be in the region around the GPS station, and it depends how high the antenna is. So if you have an antenna on a very tall pillar, you're going to get reflections from much further away than if you had an antenna down on the ground. It's only going to record for the nearest few meters. I think I don't know the answer to your question to how close we are, because we haven't really, we've realized that it's difficult, but we haven't tried very hard. So I don't know how difficult it's going to be to pull it out. I think there's a lot of neat projects that we could do by putting in a few extra stations specifically designed for looking at vegetation and soil.
Thank you, Emma, for this interesting talk. Is there a point in time that you could recall when all of a sudden these additional ways of using these tools started showing up? Did they all happen at once? Did it snowball into place? Or all this additional methods of finding this?
No, they've come quite incrementally. And the tropospheric water vapor, that's something people have been aware about it for a long time. And it's mainly been a case of geodesists not having the language to talk to atmospheric physicists and vice versa. So we knew we had cool data, but we didn't know how to use it, and they probably didn't know we had it. The ionospheric tsunami also, I guess that mainly came around in 2011. We had some idea that in theory we might be able to record these, but no one had done it until the Tohoku earthquake offshore Japan. And then the Japanese had such a beautiful network that people were able to really nicely record the atmospheric tsunami from that. And since then, it's been kind of picking up. The reflection work is really the last few years. And that's a little slow to take off, I think, because it's not intuitive for some people to like, what we can use these the thing that Multipath's been like the bane of our existence for decades, and suddenly we might think it's useful.